I didn't get it.
And you may begin.
Okay, thank you. Okay, welcome everybody. Thank you for coming. It's a great pleasure to have here today Dr. Alex Smola from Carnegie Mellon University. Dr. Smola actually has been sort of on a whirlwind. He started out, of course, he went to University of Technology in Munich and University Degli studied Pavia in Italy, and AT&T research at Homedale, and then he also was at the National University, Australian National University, sorry, where he was in the Research School for Information Sciences and Engineering, and then he moved as a senior principal research and program leader at the Statistical Machine Learning program at NICTA, which is is that in Canberra?
Yeah.
Yeah.
I didn't actually change my office. I just changed.
Well, they're just right next to each other. I've been there. Yes. From 2008 to 2012, he also was at Yahoo Research, and then finally moved to Google Research, where he spent a year, I guess, waiting to move on to CMU, where he's currently professor in the research in the machine learning department, which I understand is a department within the School of Computer Science. And again, he still consults. He still consults for Google. So, and of course, he's well known in the area of machine learning, and he's edited and written several books and papers. And with that, I'll let him take over.
Okay.
Thank you for coming.
Okay, so many thanks for the kind introduction. So just to clarify a little bit why you see CMU and Google there. So I work part-time for Google. Actually, I have an intern's badge, and when the internship movie was made at Google, I thought this was particularly amusing because this was about a 40-year-old intern, and I figured, well, they made the movie for me, right? In any case, this is just the easiest way how Google can handle those things. So this work is, to some extent, background material, an overview, but putting some of the work that we've done into context there. So I just figured it was probably a good idea to give a slightly broader context. There will not be many equations harmed in the beginning. The math will happen towards the end of the talk, or I'll run out of the talk, in which case I can explain the stuff to you later. But there's actually math that goes with this, but I think it's probably a better idea to convey the intuition and how the algorithms work, and then you need to read up the proofs on your own anyway. So there's, yeah. Secondly, at any time if you have a question, something's not clear, raise your hand, ask. Talks for you. I presumably know what I'm talking about, at least I can pretend that, but I want to make sure that you get something out of the talk, so ask if something's not clear. Right. So, for instance, can everybody in that other classroom over there, wherever that is, hear me? Wave your hands if you can hear me. Awesome, thanks. Good. Yeah. So, now let's start with something very simple, namely a vector space model. And the reason why maybe those first set of slides are a little bit more text-focused is because I figured, well, we all can sort of kind of relate to what text does. So it's, a nice, case where we can, look at things. So this is probably one of the first papers that actually kind of nailed this. This was a paper by Salton, Wong, and Young, and it's still cited. And, I mean, if you look at it, this is a very long time ago, right? It's 35 years ago. And so basically, well, almost 40. So this is essentially, this paper argues that, take a document, take all the words that occur. Let's say the word machine occurs twice and the machine learning occurs once. And so I have machine, 2, learning, 1, and, probably 20, and the maybe 15, and so on. And you basically just turn this into a very high-dimensional sparse vector. This sounds horrible, because it's just bag of words and it would scramble things a lot. And if you think about all those T-shirts about grammar saves lives, such as, well, let's eat grandma and let's eat grandma, right? you can imagine how much worse it is if you just scramble everything into a bag of words. Mind you, CMU actually has its own bag of words. I just forgot to take a picture of it. It's a bag with words in it. Some student art. This is basically, as dumb as it seems, still one of the most used tools if you want to analyze text. And if your algorithm can't beat that as a baseline, you have a problem. Okay, something slightly more recent. So he's actually my manager at Google, Andrei Broda. And so he won the Kanellakis Prize last year. I mean, it was announced something like end of last year, beginning of this year. He, together with Moses Charikar and Piotr Indik, those three won the Kanellakis Prize. Now, what does it say? This is one of those great prizes that, you're really lucky to get. And it basically is a major contribution to theory and practice in computer science. And effectively, they got this prize for their work on random projections. And so, given that, I figured, well, maybe it's a good idea to look a little bit at how these tools from computer science also map fairly nicely over to machine learning. And, okay, I managed to squeeze in a couple of my own results in this context. Don't worry, I'll explain how it goes. So, I'll start with something very simple. Let's say I want to distinguish green ham from red spam, right? And I have a linear classifier. So, well, this would do a good job, and this one would do, and this one as well. So, and of course we know this is the one to rule them all because it's the large margin separator. But the point is basically all of those algorithms and naive Bayes, by the way, as well, at some point, if you write it in the right way, require an inner product. Okay, sounds pretty innocuous, right? If I have 200 words in my document, no big deal. The problem is that in some cases this is still a big deal. So if you have very long documents, 2,000–3,000 words, and if you have a lot of documents, you need to do a lot of processing, this can actually be a chore. And so the obvious question then is, are there ways how to make this cheaper? So cheaper can mean a lot of different things, and those different things will lead to slightly different algorithms. So cheaper can, for instance, mean, can we make it faster to compute? I'm not going to care that much about this here. The question that I will care more about is, well, can we do it with less memory? And related question is, can we solve this in a lower dimensional space? Mind you, those two things are not quite the same. Because sometimes to get to this lower dimensional space, I have to use a lot of memory to get there, which kind of defeats that purpose, but it still may be better there. More sparse and faster to compute often relate to each other. However, not entirely, because as we all know, dense matrix linear algebra is about 10 times faster than sparse linear algebra. This actually has hardware reasons. It has nothing to do with how good a programmer you are. It has simply to do with the fact that burst reads in main memory are about 10 times faster than random reads. And yeah, the numbers differ between a factor of 5 and a factor of 20 depending on your computer, but that ratio has kind of stayed the same throughout. So even if you are, Jeff Dean, who is probably, one of the world's best programmers, there's only so much you can do. So maybe in some cases you care about doing this computation when, two strings or, two similarity measures are really very similar. And so the thing that binds them all together is to use randomness, in this case random projections. Right? So as said, very few theorems will be harmed, essentially none in the first part of the talk, more towards the end. So towards the end you'll need function analysis, but for now let's just look at locality sensitive hashing. So here's the basic idea. So let's say I have some data x, right? This may be very high dimensional in tens, and I would like to do something with this in such a way that this lower dimensional object then preserves most of the interesting bits about x. So then what I can do is I can take this long vector, take a projection matrix, and get a small vector out of it. Okay. So compressed sensing, by the way, does that too, where we have sparsity here, we have some suitably chosen incoherent matrix or whatever of that form here, and then we get something lower dimensional, possibly dense, and with suitable assumptions, I can tell everything about this X from Z, even without ever having seen X directly. So compressed sensing, for instance, does similar things. But in their original setting, and there's a couple of really nice papers by, for instance, Indik, Aklioptas, Imorlika, Motwani, Dasgupta, and others, and there's a really nice elementary proof by Dasgupta and Gupta from 2002. If you haven't seen that one yet, I'd very much recommend that you do. It's a beauty to read. It's like 1 page, 1.5 pages, and that's it. And it basically says the following thing, that with high probability, the distance between any pair is well approximated from below and from above by the projected distance. Right? And that's actually a really useful result, because that means if I can approximate distances fairly well, then I can also do, things like inner products fairly well, just by polarization. So the second binomial formula, x minus y squared is x squared plus y squared minus 2 to x dot y, and so that means that if I get the distances right, I also get inner products right, with some suitable care about scales and so on. Okay, so if I do this, then nothing easier than that, and there's probably about one paper in a machine learning conference that attempts to at least get accepted there, which has the, quote, brilliant idea of, let's use locality sensitive hashing to solve, linear classification faster. And I'll tell you in a moment why I said, quote, brilliant idea, because actually this is not really necessarily making life easier. So if I have a very high dimensional but sparse vector, let's say I have, maybe 100,000 possible words in my dictionary, and my document only contains maybe 100 non-zero words because it's a very short email or whatever, then projecting into a 1,000-dimensional dense vector, I've actually lost a lot of, I've actually made my life a lot worse, right? Because basically now I have about 10 times as many non-zeros, so even my linear algebra library will run no faster. Secondly, I've lost some accuracy simply due to the random projection. And furthermore, it also requires more memory storage, so basically I've made things uniformly worse. And this is usually the reply that I give authors who submit such papers. And unfortunately, I've had to do that more than once, so I hope you won't fall into this trap.
We'll know who does that.
Yeah, you know who to blame for it, yeah. So I've given it away now. Okay, so, but, obviously, the nice thing is that, in this lower dimensional space, you can do certain operations more cheaply. And sometimes, for instance, you can actually use things like that for matrix inverses and all sorts of other tricks. So there's a lot of really nice things that you can do there. So this, for instance, has gained recent popularity also in a really cool paper by Halko, Martinson, and Trop, where they basically, it says something like finding structure in matrices through randomness, and that paper is essentially 3 parts. The first part is the very heuristic part of here's how you do it, and that's very easy to read. Then comes the part of, here are some theorems, and that's a little bit more challenging. And then comes the real fun part, namely the entire appendix, which is more than half of the paper, which is a tour de force through really cool concentration of measure results for matrices. And to some extent, that's actually the most valuable part of the paper. The other part is also good, but you'll probably learn the most if you try understanding those proofs. But the problem is that this actually is not so great, because any sparsity that you had initially is gone after that, and also this projection matrix P tends to be dense, and you either need to store this matrix, which will require an inordinate amount of storage. So let's say we go from 100,000 dimensions to 100 dimensions, right? So then we are talking about 100 million floating point numbers, right? So that you need to store. Now that is about 800 million bytes, so it's close to a gigabyte. It's not so much fun. On top of that, you need to store the index structure and everything. So in practice, I think you'd be hard-pressed to do this in less than a gigabyte. So you've actually made your problem worse. Can we do better? Basically, yep.
You can store a matrix with, let's say, the seed of a random number generator.
You're absolutely right, and this is what you could do. So basically, what you're already getting to is the issue of hashing, and so great question, and I would have thanks. So I didn't have to define this. This is awesome. Because basically what you can do is you can get away without storing this matrix. What you could do is for each matrix entry ij, you could just have, random number generator of ij. Computer scientists call this a hash, so hash of ij. And then you can do interesting things with this hash. You treat it like a random number. So essentially what you're doing here is you're trading off memory versus computation. So for the memory lookup, you may have to do burst read, and you pay maybe 10, 20 nanoseconds for it. Otherwise, your CPU core will have to do some non-trivial computation, and you might get about 10 clock cycles. So in other words, if your hash algorithm takes less than 10 clock cycles, you're in good shape. And this is kind of a close call. My suspicion is that storing it in memory is faster because your linear algebra library is optimized for the latter. So unless you want to go and rewrite Atlas, probably storing it is better. Yep?
So why are we expecting C to be sparse?
Well, because we're dealing with documents. We're dealing with user behavior. We're dealing with a lot of natural data where we have a large number of discrete actions. So if you were dealing with images, Z is not sparse. In that case, you may actually have real gains. However, in that case, Z may already be, a couple of megapixels. So the projection matrix would now be 1 million at least by something, and storing it would be even more painful. I'll show you later on how I can generate random matrices that behave almost like random Gaussian matrices, but are much, much cheaper to store. As a matter of fact, you don't have to store them, and where it's much, much cheaper to multiply with them, namely, rather than quadratic, you have log linear time to do the multiplication. So this is towards the end. But you probably had another question.
Right, so if Z is a projection, result after the
Yes.
projection, I mean, I can expect the original data to be sparse, but not the projected.
Correct.
Right?
Yeah.
Yes,
So
that's true.
Say when you say killing sparsity in Z,
Yes.
then
So, yeah, basically it.
Means the
Well,
same.
it's basically not sparse. This is dense. So you.
okay.
Okay, this was maybe unfortunately worded, but yes, you start out with something nice and sparse, you end up with something fat and dense, and you've just made your life harder. So here's a really cool trick that Andrei Broda and a few others proposed. It's called Shingles. No, it's not contagious. So who has heard of Shingles before in the computer science context? Okay, cool. So yeah, most of you are going to see something new. So here's the idea. I go and take hashes of all the non-zero coordinates of this vector, right? So that gets a hash, Quick, Brown, Fox, they all get a hash, right? And then I store, let's say the 4 words that correspond to the smallest hash. Sounds crazy, right? Like the Brown, Fox, the. So I count them. Right? I'll get this. Now, let's say there's another phrase. The quick brown hedgehog had breakfast. I do the same thing here. And yeah, voila. Well, that will match. And that's about it. So now I can go and compare those, and try to identify, therefore, how similar those two phrases are.
Quick question.
Yep.
You expect these hashes are the same?
Um,
Jumped and had hash to 10, and you didn't use that as one of your smaller hashes in the first example? Is it just a typo?
No. So the fact that jumped and had amount to the same number is, well, okay. Yes, okay. This should be a number less than 10, yes. This should be like 8 or 7 or whatever. Otherwise, it's wrong. Yes, you're absolutely right. Sorry, I need to fix this typo next time I give this talk.
But the jumped and had should, the hashes don't collide, or do they?
So they can collide, obviously, because it's a hash function. Obviously, I want to make sure that the probability of collision isn't that high. But the fact that I put jumped and had and gave them the same hash ID was on purpose to demonstrate that, yes, you can get collisions. So typically what you would do, and this is a very simple thing, if I have an alphabet of size n, then a hash function that covers a range of n squared is good enough, and that's just due to the birthday paradox. If you don't know what the birthday paradox is, go to the Wikipedia page on it. You'll enjoy it. It's really fun. Anyway, but obviously what I'm assuming is that different phrases, if I apply the hash to the same word, will give me the same hash value. Okay. So the basic idea is, you hash the coordinates of the non-zero vector, keep the k smallest hashes, and then you estimate the Jacquard coefficient by just looking at the Shingle overlap. Let's say, these guys here, this is just already ordered by, Shingle ID, and without loss of generality, you can always make them consecutive. Now they just count the overlap. And so, of course, this is going to depend on, how many shingles I pick, and it will also depend on how similar those strings are. Right. Now, this you can fairly easily verify in expectation will give you exactly the Jacquard coefficient. Because without loss of generality, I can assume that my entire alphabet of words is the set of words occurring in the union of both strings. So that takes care of this part here. And then the probability of overlap is really just, whether some words are in common for some random subset. Because basically picking the k smallest just means pick a random subset. Okay. Now, conditional random sampling is then an application of this to, inner products. So this is a very cute paper by Lee, Hasty, and Church from 2006. They had a NIPS paper, and then Ping Li wrote a couple of other very nice follow-up work based on this. And so the idea is, and this is quite clever beyond what the original Shingles paper did, the value of the hash lets us actually estimate the non-zero density in the set. In other words, if I have a lot of words, then the smallest of the k hashes is still going to be fairly small. If I have very few words, then the smallest of the k hashes is going to be large, right? So for instance, for string A, which doesn't have many words, the smallest of the k hashes is 8. Here, the smallest one is 4. So this lets me compute more than just the Jacquard coefficient, but I can actually compute inner products, at least estimate them. And you can do a few clever tricks in, using the fact. Well, basically the problem is that, what are you going to do with the largest term? Are you going to use it, or are you going to throw it away? What it actually is, and I just use that for the density. And you can squeeze out a little bit of extra information, and Ping Li wrote a bunch of papers on, how much you can squeeze out there. So very nice papers if you want to read them. So here's what's really good about it. It sparsifies the vector a lot more. So if I have, a couple of books or long web pages, and I very quickly want to find out, are those web pages similar or are those books similar? If the shingles don't match, I immediately know, well, okay, this is hopeless. If they match, then I know with high probability that they are quite similar, and then I can invest more work. So this lets you very, very efficiently throw away a lot of content that's obviously dissimilar without really looking at the full content. It's a very sparse, it's a very smart compression, because on very sparse vectors, it preserves most of the vector, and on very long vectors, well, okay, it just, picks whatever. It makes the inner products go much faster. However, and this is why I'm actually not so fond of it in the context of where Ping is actually advocating its use, it does not really reduce the dimensionality. The only thing is it makes the vector sparser, but quite often your documents are already quite sparse anyway. The dimensionality reduction issue is more from the fact that you have a fairly large vocabulary. And as soon as you tensorize that with all the users that you have in your database, let's say I'm Facebook and I have 1 billion users, and I have maybe a vocabulary of maybe 1 million words that people will use, well, then I have basically 1 trillion coefficients that might potentially be meaningful. Okay, most of them are going to be 0 anyway, but if I do something very stupid, I would have to store 1 trillion floating point numbers, which is a non-starter. So you want to be able to use mechanisms for compressing this efficiently without really giving away too much information. And I'll show you in a moment how to do this. The other thing that's a little bit of a problem with this conditional random sampling is that actually, as soon as I perform what amounts to otherwise kernel expansions, this aggregation becomes a lot less trivial, and you are back to a lot of the problems that you started with. But if you just want to compute, inner products between vectors, this is a brilliantly elegant idea. Okay. Any questions so far? So now we'll look at hash kernels. So this is hash browns with kernels. Apparently, at least so thinks Google. So let's just recall LSH, right? The issue was that we had this dense matrix here. We took the sparse vector, and this dense matrix destroyed all the sparsities that we might have had initially to give us a dense vector here again. Right? This was, really a problem. And the problem is that, storing this P is expensive, and as already mentioned before, yes, I could use a hash function, but then I trade off memory for computation, and that may not be such a good deal in the end. Maybe on a GPU it would be a really brilliant idea. On a regular PC it's probably not such a great idea. And on top of that, it actually does more than what we want. If you think about it, it's actually preposterous to assume that maybe a couple of thousand coefficients will do to do the personalized spam filtering for a user base of 1 billion. And, we can actually store in my memory something like maybe 1 billion coefficients. So why reduce ourselves to tens of thousands if we can actually store 1 billion? So basically, can we fiddle with this such that it's just, such that this vector is just small enough that we can do something with it, but where this operation now is much cheaper? That's what I'm going to show you now. So let's take a very simple case, personalized spam filtering. So this is, still from my time back at Yahoo. Okay, and I just didn't have the heart of changing Yahoo to something else, right? Yeah. So let's say we want to do spam filtering, and we want to personalize the spam filter for Barney, right? So, everybody gets his own parameter vector, and we'll have one global consensus parameter vector. So what I would therefore do is I would, have a consensus weight of, whether the word mention implies ham or spam. So I basically do a dictionary lookup. I find out that mention maybe has token ID number 1, and that, the word mention concatenated with Barney. So basically Barney's weight for this is concatenated at maybe position 20 around here. And I do that for each and every word, and I get this sparse vector. Now, as already mentioned, this is in a very, very high dimensional space, which is basically vocabulary times user base. And you could just build a linear classifier in that space, and actually people have done this implicitly by some multitask learning papers. So there's, for instance, this paper on amazingly simple multitask learning by Hal Daum, where he effectively does this with a 10-line Perl script, and it works well for like 1 to 10 different tasks, but it doesn't work terribly well if I have 1 billion different tasks, right? Like for spam filtering. So here's the thing that we did. We took a hash function, and so for each non-zero term, we compute the hash of that location, and we map it into a more sparse vector. So I might get some collisions. So this is, for instance, why here you have a 2, and there you will get a 3, because maybe 2 of those guys collided. And then, yeah, okay, so you know that. But here's what you can do. You can basically skip that dictionary part entirely. Because it's kind of stupid to first, find the token ID for a word, or that word and use a Barney, and then throw that token ID into a hash function just to end up with some random location here. So the beauty of this is that I never really need to store the dictionary. I just need a hash function which ingests directly the word mention and Barney and gives me some location. The other thing that I added is we added a Rademacher hash, which is basically just a 1-bit hash, which is either 1 or -1. And the reason for this is that, first of all, it makes the analysis so much easier. The theorems are a little bit tighter because you remove the bias. And third, it actually works slightly better in practice. The way how you implement it is you just compute the hash, you take away the most significant bit, use it for the sign, and you use the remaining bits for everything else. Don't reuse bits, otherwise you get really messy things. And then after we did this, we realized, people before us knew that already. So this is a paper by Charikar. Remember that name? This is the Kanellakis Prize winner, Chen and Farah Colton, who actually proposed that in 2003. Yep?
But if you don't use a dictionary, you will lost some good probability for the natural language processing, like synonym and like stemming, those kind of stuff, right?
Yes and no. So if I don't use a dictionary, so there's a couple of things that I can do. First of all, I can actually take substrings. And so I could have the word, I could have the stemmed word, I could have, substrings according to, whatever other meaningful extractor that I have, and I throw them all in as features. And the good thing is that now I don't need to keep track of all those features anymore. I can just, use them. So this makes life a lot easier. It also means that this auxiliary data structure, which is usually the dictionary, that's the one that usually uses up most of the memory on your machine. So you're usually wasting most of the memory for stuff that you don't really need to build the model. Here I can use all my RAM to really store the model as opposed to any auxiliary stuff. This is probably the biggest benefit, because usually building that auxiliary data structure is what makes it really slow to implement something. This is the place where it's failure prone. Unless you're really brilliant, you will waste way too much memory on it, and on top of that, it makes the algorithm slow. All those problems are gone. So that's basically the advantage. And on top of that, the resulting vector is still sparse. It has no more non-zeros than the original vector. It might have a bit fewer if I have a collision, but those collisions are very infrequent because I map into something still very high dimensional. So the good thing about this is I don't even need to know the vocabulary beforehand. So if I all of a sudden acquire some users who start speaking Klingon, well, that's fine. I hash it. I mean, it might collide with something else, but that's with very low probability that it'll collide with something very meaningful.
That means if you want to do text mining, you don't even need a natural language processing facility.
No.
By using this
No.
Because you take the raw word, then just do a hashing, right? Then you get what you want.
Well,
already.
almost. That would be a bit too radical. I would not do this. What I think is probably more appropriate in this case is you use the NLP tools as a preprocessor to extract corresponding attributes. So for instance, what I might do is I might use an LDA annotator to annotate topics for all the words, and then I perform estimation in the product space of words and topics. So I wouldn't only have the words, but I would have the words and the topics attached with them. I would also have the words and the user. So I can actually now work in much higher dimensional spaces than what's usually computationally feasible. This, by the way, I think is one of the reasons why usually people did not work in the product space. And actually, if you do, you get benefits. So for instance, for some advertising and a user targeting application, working in that product space gave us another 0.5% or 1% lift, which basically means more money at the time for Yahoo. Okay, so here's what really happens. Let's look a little bit at the math. So don't worry, it's not going to be very technical. It'll get more technical towards the end. So this is our matrix. It's maximally sparse in the sense that each column has exactly one non-zero. I need to have at least one non-zero because otherwise, it's just means ignoring those words. And they will have signs 1 or -1. And that's basically what we have. So this is a big difference to LSH. It does preserve the inner product in expectation, and you can work that out just directly from the Rademacher hashes, because these will in expectation not agree unless unless those two guys match. And that's it. So the proof is very simple. What it means in practice is that in the original space where you had orthogonality, you preserve orthogonality with high probability in this lower dimensional space. This is just a simple application of a Chernoff bound. So if you don't know what a Chernoff bound is, look it up on Wikipedia afterwards. It'll help you with a lot of your work later on. This is one of those really cool bounds. So that's basically what it is. And this result you can get with one line.
So what numbers are we looking at to basically guarantee this probabilistic result?
Basically, you get a rate of 1 over square root number of dimensions in terms of the guarantee. So you want it to be large. 1 million is good, 1 billion is better. But it goes like 1 over square root number of those dimensions. The other thing is, and this is quite nice, whenever we had a direct sum before in this Hilbert space, we now just get a sum in this hash space. So this is kind of really useful, especially if you want to do complicated constructions in your Hilbert spaces. This actually reduces it into something that you can compute fairly easily and afterwards. And you do all your beautiful analysis here, and then this is how you implement it. And yeah, they then gave a refined analysis. Remember that name? He'll come up later on at the end of the talk also in some joint work. Yeah, Tamas is really, really smart. And yeah, that paper has some of the references. Now let me show you that this is actually useful. This is a small data set, right? 20 million users, 20 million emails, 400,000 users. This is a small toy data set. Yeah, and obviously, I cannot tell you the spam rate because that would have been giving things away at Yahoo. So basically, the baseline system had a spam rate of 1, which is, I don't know, some percentage of emails that get through in spam. And this axis basically shows what happens if you increase the dimensionality of your hash space. So 2 to the 20 is 1 million, right? 2 to the 22 is 4 million, 16 million, and so on, right? And so obviously you actually would have quite a few collisions here, but nonetheless it doesn't really hurt you very much. So the blue line is basically what you get if you use the original unpersonalized data and you solve the problem in hash space, and you can basically see that around 4 to 8 million dimensions, this is pretty good. Of course, if you are in a low dimensional space, you lose, but you don't actually lose that much. The cool thing is that for this personalized curve, we could not have solved this problem exactly, because this would have been in a 400,000 by, 100,000 dimensional space. This would have been very costly to solve. So while, yes, more dimensions are better, there's a limit to what you can computationally afford. So that sounds good, right? But here's actually a problem, right? So if you look at the users, then most users don't label their data, their emails. Who's recently labeled an email as spam? Okay, good. So I think we're probably around here in this room. But, okay. I hope I can convince you that actually labeling your emails as spam helps. So here's what we did. We looked at the stratified results of, depending on how many emails you've labeled. And of course, you can ask, what does it mean to be able to infer whether an email is spam or not spam if a user didn't label anything? Well, we have auxiliary signals, and on top of that, you can just leave that labeled email out of the training set. And what you can obviously see is the more you label, the more your personalized spam filter will pick out your particular spam. So for instance, if I think administrative emails are spam and I label them as spam, it'll at some point pick it up. But it also means that everybody benefits, even those users who didn't label at all or labeled very little. So here's why. Actually, does somebody have an idea of why this helps? Why do the users benefit even if they didn't label anything? Well, we also have spammers, right? They label their stuff too. So what happens is that this is effectively the machine learning equivalent of the kill file. Okay, who knows what a kill file is? Okay, so in the old days, when you were an internet troll, you could, go and post to a forum and, you'd annoy people, right? At some point, the administrator of the forum would decide, okay, well, user alex.smola@gmail is not welcome here anymore, and well, basically my posts are just blocked, or maybe my account is gone, or whatever. And then I would go and register an account, alex.smola2@gmail.com, and I would repeat the same thing, and alex.smola3, and so on and so on. So basically, that thing got old fairly quickly. Now, what you can do, though, is, this is what people realize at some point, well, you can just set it up in such a way that the troll can read his own posts, but nobody else can. And so, since trolls are usually not the smartest guys, they will then think, okay, well, I'm posting all those things that are really important and nobody else cares, so let me go away and go somewhere else, right? So basically, this is a hand-tuned, personalized content filtering. The spam gets to see his the troll gets to see his spam, and nobody else does. Okay. Now, spammers want their emails to go through all the spam filters, right? So they mislabel stuff. And what happens is, this way, the spam filter learns for the spam to let all the spam through. But nobody else is affected, or only affected very little. And this is why you see the gains here. And also, maybe Alex has a really bizarre way of what he considers spam or not. Maybe I hate all administrative emails, so I label everything as spam. Whereas other people love administrative emails, so they'll not do that. And so that's why my bizarre email preferences might not really harm everybody else. Okay. So I just wanted to get to the point of, well, do we need an NLP toolkit? Yes, you do. And here are, for instance, all the ways how you can get, those things with wildcards, and then you just, map into fragments, and you put them into the same filter, and it works too. Okay. I should probably skip. So actually, how much time do I have?
You have about 15 minutes.
Okay. So in this case, let me skip over this sim hash and clustering, except that I want to show you this really basic idea, because two teams of authors have gotten a fairly prestigious prize based on a very, very simple idea. So the first paper is this paper by Gurmans and Williamson. And if you've not read this paper, it's a delight to read. You absolutely should read this. It's on semi-definite programming and a really brilliant way of using this for graph cuts. Read this paper. Anyway, here's the idea. If I have two vectors, then if I pick a random hyperplane, then the chances that both vectors lie on the same side of the hyperplane is proportional to the angle in between. As a matter of fact, the probability that they lie on opposite sides of that hyperplane is proportional to this angle divided by pi. You can see why it's pi, because once I flipped around by 180 degrees over pi, then same story again. Okay. Now, what Gurmans and Williamson did is they used this for an SDP relaxation to show that their relaxation can then be used with high probability to find a near optimal solution for the problem. And this was a big breakthrough. And Charikar, actually, I think he did this while he was an intern at Google. Or maybe he worked at Google at the time, but his code is in Google's code base. He basically realized, well, actually, let's just store for a set of random hyperplanes the probability, the information on which side I am. So these are just one-bit information, pieces of information. And this now gives me a very compressed representation of this vector here. And then to find out, what the angle between two vectors is, I just need to compare those bit strings. By the way, this is making a comeback now, or is being reinvented under the name of one-bit compressed sensing. So if you've heard about one-bit compressed sensing, this is the same thing. And then, of course, if you have this, you can design, a very efficient angle computation mechanisms by just, doing this here. So you basically just take, the length. So you basically use, just standard, definition of inner product, length of the vectors times the cosine of the angle in between. Now, why do you care? Because computers are insanely fast for comparing bit strings. As a matter of fact, all Intel CPUs and AMD CPUs that are at least a year or two old have this hardwired as one of the really fast computations in there. So it's the SIMD or AVX or whatever you call them instruction sets. So this is fast. So you want to exploit this. We actually use this for clustering, and I'm not going to go into the details of exactly how this is used there. But basically, the issue is if you have a lot of documents, then if you want a lot of clusters, if you want to figure out which cluster goes where it belongs to, doing a brute force search is super expensive. So without going into all the details in the Metropolis Hastings sample and a lot of other things in there, you get that improvement in runtime. This is a log scale, so you get like 1 or 2 orders of magnitude. This is the point where it's worthwhile, and the more important thing is that something that was the dominant aspect in the runtime turned into something that's kind of the minor aspect, and we could have gotten a further improvement if we'd tuned the other pieces, and we're actually working on the latter. But basically, this is when it pays off to attack things with hardware knowledge. If you're getting an order or 2 of magnitude improvement in your algorithm by knowing what hardware your algorithm runs on, you should do it. If you're getting a 20 to 30% improvement, don't bother, because it's just not portable enough. Okay, what I want to show you is, in the end, a little bit about how kernels fit into this entire thing. We've seen a little bit about kernels already, but just a little bit of a refresher here. So sorry that this was a little bit too fast, but Hamid is going to have all the slides anyway, so you can go through this, and there are papers for all of this that you can read on. So, well, we all know about kernels, I suppose, as in, they are this weird and wonderful tool by, you take the data, you map it into high-dimensional space. Well, my drawing skills aren't so amazing here, but basically the idea is you map into a 3-dimensional space, and now I can separate the circles from the triangles quite cleanly. So that's all really good, and we had a good time writing lots of papers about how to kernelize stuff. The downside is that at some point, well, you start realizing, as I get a lot of data, well, this is actually costly. So it's another example. So this is exactly those 3-dimensional features. I map x1 and x2 into x1, x2, x1, x2, or x1 squared, x2 squared, x1, x2. That all of those would do. But the problem is, while the representer theorem already tells us that the number of basis functions now increases linearly with the sample size. This is really bad news. Because as it increases linearly with the sample size, it means that I will have to deal with larger and larger kernel matrices as I do optimization. Which explains a little bit why over the past 7 to 8 years, kernels have gone a little bit out of fashion, at least straight kernel methods. So then people realized, well, actually, there are ways how to fix this, and the first generation of those reduced set algorithms basically said, well, let's train on the full set and then, compress things down. And since we are talking about Hilbert spaces, I can use all geometry, and you optimize, and you get this reduced set. And it works kind of nicely. But you still have that cost at training time. And if I have, an n by n matrix, a, well, not so smart algorithm might be cubic in that. So it's not good. So then came all those reduced rank papers, and probably the most beautiful one is the one by Kempe and Das. I think they actually got the best paper prize for that. The second most beautiful is this one here. I think they're somehow ordered in order of beauty. So, mind you, this is the best known one. Where basically you would go and pick a lower dimensional space already before you really invoke your optimization library, and then basically this is just like doing PCA, but you pick explicit basis functions onto which you project, and so you do Gram-Schmidt, and it's usual geometry and linear algebra. Okay. Doesn't really matter very much, but the problem is these algorithms still were fairly costly because you had to deal with, essentially, this kernel matrix here, which is, smaller dimensional, maybe, a couple of thousand dimensions times, this full thing. And so if I have n dimensions of n basis functions in d dimensions, the cost would have been order n times d at the very least, possibly more. So then people, went back to primal space, and a really cool paper was the paper. Actually, both papers are really cool. This paper by Radford Neal has the infamous property of having been rejected from NIPS and having been essentially the starting point for Gaussian process classification and regression algorithms. So it's one of the most impactful papers in the area. The original paper got rejected, and then probably about 100 papers that built on this work were accepted at NIPS. Happens, right? Now, the point is, though, that, let's go back to primal space. This is essentially destroying all the beauty of kernels. I just go and pick those random basis functions directly. And so this paper by Radford Neal showed that if I, let the number of basis functions go to infinity with suitable weighting, I get the Gaussian process in, the functions that I can parameterize. I mean, he wrote it in the context of neural networks in infinite number of hidden units, but that's basically what happens. Rahimi and Recht then picked this up in 2008, 2009, where they said, well, let's actually do Fourier analysis, and we'll get to that in a moment, for, let's say, the translation invariant kernel, like the Gaussian RBF kernel, and draw from the Fourier basis. And if I draw from it in a suitable way, then the kernel that I get effectively converges with high probability to the Gaussian RBF kernel. So that's kind of state of the art there. So naive is really expensive, and this is sort of kind of the best thing that you can do, but basically you still need to decide, how many basis functions do I need, and for each of those basis functions I need to store d coefficients if I operate in d dimensions. So the cost is something like, sample size times number of basis functions times dimensions, and then the memory requirement is number of dimensions times number of basis functions. So what I'm going to show you afterwards now is an algorithm that will reduce this from m times n times d to m times n times log d, and here it'll be just order n. So d will turn into 1 and log d here. So this is much smaller for very large d. Yeah. So it's kind of funny at ICML, the referees complained that we didn't show how much log d was smaller than d. Okay, we did. So that's why you have a rather weird set of results there. So now, this is probably the most mathematical slide in the entire talk, so don't despair if you get intimidated by it. Basically, here's what happens. If I have a kernel that's invariant under a group action, then I can expand this kernel in the corresponding irreducible representation of the symmetry group. So I get this thing here, where these are, corresponding subspaces. And what it means for translation invariant kernels, because, they actually have an abelian group, so this is all very nice. It's also Lie group. So I can basically write it through this Fourier basis. This is very, very convenient. And so then the idea is basic, and, for inner products, you get those spherical harmonics, and you can do corresponding things, and I'm not going to bore you very much with that. But basically, you end up having to draw from that spectral density if you want to get an approximation. So this is what this paper did, and this is a lovely paper that I wish I had the idea before they had it. It's really a cool paper. So you basically go and draw the frequencies from this spectral distribution, and then you just take inner products in this Fourier basis. Obviously, you don't need complex numbers, but just written it out like so for simplicity. Now, for Gaussians, you draw from a Gaussian, and in general, you have a spherically symmetric distribution, and then you rescale. And for the moment, we are going to focus just on the Gaussians, and that'll become clear in a moment. So basically, if you think about it, the dominant cost is to then store this Gaussian projection matrix, that's order n times d, in terms of CPU and order n times d in terms of memory. So you could get away with smaller memory footprint by using exactly this hashing trick, but I don't think it would do you any good in terms of speed. So the idea is, can we make this smaller? So what I'm going to propose is a hack that I think is going to be useful considerably beyond just kernels, which will give you something that looks and feels like a Gaussian random matrix, except that it's much easier to handle. And yeah, this took a couple of years until we had that specific form of the matrix. As in our first attempts a couple of years ago were not successful, and then in the end we figured something out. So here's what we do. Who knows what a Hadamard matrix is? Okay, Hadamard matrix is basically like I'll show you pictures in a moment on the next slide, but basically it's a matrix that you can multiply with in log linear time, and it's a matrix that basically scrambles dimensions. It's a orthogonal matrix, you can normalize it, and there's the fast Hadamard transform which runs in the same time as the fast Fourier transform, and more importantly, there's a website called spiral.net, and you tell it, well, I would like to have Hadamard transforms on this hardware, and please generate me some C code, and you download it, and it's fast. Don't use the Hadamard transform in MATLAB. It should be called the slow Hadamard transform because it's actually slower than matrix vector multiplication, which is kind of an embarrassment. So here's what we do. So remember, we want to have a Gaussian random matrix, so where each of the entries are drawn IID from a Gaussian, from a normal distribution. So we first take a diagonal matrix with binary entries 1 and -1. This just decorrelates things, makes some of the analysis a little bit easier. Then we take this Hadamard matrix which scrambles everything. We then use a permutation here. Because we are going to apply another Hadamard matrix later on, we want those two to be incoherent. And then we multiply with a Gaussian diagonal matrix. This Gaussian diagonal matrix in the end is going to have the effect that everything looks Gaussian. And then for good measure we rescale to have different spectra for different kernels. Okay. So before I go and talk about the various properties, the first thing to realize is that storing this object here is order D. Why is it order D? Well, this is order D. This I never compute or store. This is just hard-coded, right? This is a permutation. It's order D, diagonal, no computation, diagonal. So you never ever instantiate this beast. You just keep the various bits and pieces. And then computing it is D log D. So if I have several of them, you stack them up. This is what the Hadamard matrix looks like. It's basically 1, 1, 1, -1, and then I just replicate it. So I can, in this case, I can prove that this is all correct and all is good. The more interesting thing is that if I have different spectra, like for instance a Matern kernel, I can, in the spectral representation, actually generate those scaling coefficients very cheaply. Again, details are in the paper. Here's a quick example of why Gaussians are actually a really bad idea, because basically all the frequency concentrates at a very narrow band. So it's the usual concentration of measure effect. I think I'm seriously out of time here. I have 2 minutes left. So you have guarantees. And the guarantees basically tell you something like, yeah, it's okay. They're not super tight, but at least they're sanity checks, and you can prove that in expectation everything is good. The real question is, does it actually work? And so here we basically compare to random kitchen sinks, because they've already proven to basically work as well as the real thing. If you use the wrong function basis, like just an FFT rather than Hadamard, this is wrong. That's why I told you there's a longer history to how to get there. And if you use, the Hadamard features, you actually get something that looks the same as random kitchen sinks. It works fairly well. And yeah, it's way faster. So this is you would expect that, you use less memory, and, it's faster because log D is smaller than D, and 1 is smaller than D especially for large D. It works. So these numbers here are fairly unspectacular. They are just, on different data sets. We just compared the real thing versus, our approximation, and you don't really see any difference, which is good. And in case of doubt, ours actually works better. And this is the last part here, which basically shows that by changing the spectrum, you actually can gain substantially, especially for high-dimensional problems. which is consistent. So this is basically this fast food return, which is consistent with the fact that in high dimensions, well, things are a problem otherwise. So this is it. So I think I showed you a little bit how to do fast kernels. So let me conclude with this, given that everybody's already running away in the other room. I think that's a suitable slide.
Any questions?
Yep.
You think all the computation has a centralized computing environment or distributed?
Sorry, all the computation happens in the server?
I mean, like whether it's a single thread or multi-thread or distributed.
Oh, well, for fast food, it doesn't really matter very much because the memory footprint is so tiny. So you could actually, this is another good thing that now the memory footprint is sufficiently tiny that this might actually fit into the core of your CPU. So this is into the cache of the CPU, so that accelerates things rather drastically. So cache local versus hitting RAM is a big deal, especially if you are on a energy constrained mobile device like your cell phone. This is a big benefit. I'm not for sure there are really super efficient multi-threaded Hadamard transform libraries, but in general I would then simply go and process several observations in parallel. So that's very easy. Yep. Any other questions? Yeah, sorry, this was probably really fast in the end now. Spent way too much time in the beginning.
Any other questions? Yes.
I was wondering, are there any applications on the image
Speak up.
video?
Are there applications in image processing?
Yeah, that's right.
So yes and no. So basically, after I talked about this, some of the students who took my class last semester used this for essentially kernels on images. So they accelerated some of the kernels that Andrew Zisserman and co had proposed by a factor of 10 to 100.
So is that possible to sparsify the image? I mean, since in the spatial domain the image is very dense usually, when we sparsify that, are we going to get a...
That's a good question. I haven't thought of how to use this to sparsify objects yet. You actually have rather the opposite problem, that everything is fairly dense. Yeah. And the problem is, if I was to then go and select a couple of basis functions out of the ones that I got, I still have to pay the computational price for the other ones, because it's the same thing as with the fast Fourier transform, right? Right. So if I want to get, all the frequency components, I get them cheap in, d log d time. If I want to get, an arbitrary subset of k frequency components, then usually that will cost me order k times d. So as soon as k, is greater than log d, it doesn't really, pay very much to say, well, this is the only subset of attributes that I want. But this is clearly a problem if you want to stack things up, for instance.
Well, let's thank our speaker again.
Okay, good.
I need a PDF file.
Okay, so you need to give me a memory stick.